So we have one universe, and if you're saying we cannot know, I guess Kant said that, we cannot know the fundamental nature of reality, we just see things indirectly. Okay, that's a possible view, but I'm a romantic. I think that fundamental physics, people like Einstein and Schrödinger were not just building models. They thought they were trying to probe the fundamental nature of reality. Now, Einstein was very modest about it. At the end of his life, he said, well, maybe everything I worked on was a mistake, I'd like to understand what the electron is, he said. So it's always tentative, but I think there has to be some ontological basis. I think you're giving up if you say we will never know. Leibniz also was not an agnostic. He thought that God could be understood through reason, even though God is infinite and we're finite. So I'm a romantic. I think that the universe is built out of something, and in principle, I think we should try, and we might succeed in knowing, or we might never. But I think one has to try.
Yeah.
And I think saying that there is no ontological basis, that it's all, marshmallows down there, is giving up. I think this quest for fundamental understanding is beautiful and honors the human mind.
Yes. Today I'm thrilled to share with you a special recording from a live event held at University Mohammed VI Polytechnic in Morocco in collaboration with the Chair of Complexities and Humanities at Africa Business School. This event was dedicated to honoring the work of Gregory and Virginia Chaitin, two remarkable individuals who have made significant contributions to the fields of mathematics, computer science, and philosophy. They have been residing here in Morocco for the last year at the Institute of Advanced Studies, a period in which Gregory has written his latest book, Philosophical Mathematics, Infinity, Incompleteness, Irreducibility. The book is available for download for free, and the link is below in the description. As many of you already know, Gregory Chaitin is a legendary mathematician, a computer scientist. He's one of the founders of algorithmic information theory. His groundbreaking work has fundamentally changed our understanding of computation, randomness, and the nature of mathematical truth. Virginia Chaitin, a philosopher of science and historian, has made her own significant contributions to these fields and has collaborated extensively with Gregory on various projects, most notably in the development of metabiology, a fascinating field that applies information-theoretic and algorithmic concepts to biology and the study of evolution. Planet Earth is an extremely remarkable place. This is footage from the moon, and this is planet Earth. There are far more interesting things going on here. These structures over here, for example, plants, look at how intricate and complex they are. This man-made building, cities, the climate system, the immune system, they all look more intricate, more complex than, say, a bowl of stationary sterile water or a white sheet of paper. But can we measure how complex something is? Can we give a rating or compare which objects or systems are more complex than which? Mathematicians like Gregory Chaitin like to look at the world from an algorithmic perspective. An algorithm is a set of instructions, like a recipe, through which we generate new states from pre-existing states. This perspective raises an intriguing question. Could there be a recipe or a list of instructions that, if followed, would create a plant or a city? And what can the size of such a recipe tell us about the complexity of these systems? Let's take this book, for example. It is made of only the letter A repeated over and over again exactly 20,000 times. The algorithm or recipe to make this book would be extremely simple. It could actually consist of only a single line that says, print the letter A 20,000 times. Although there are 120,000 letters in this book, the recipe to generate it consists of only one line of instructions. But what about this book over here, where the letters form intricate sentences that compress a significant amount of human wisdom and experience? What could be the shortest recipe or list of instructions that, if followed, would generate the full text of this book? The size of such lists of instructions is certainly longer than the single instruction needed to generate the first book, and this constitutes the basis for a rating or a measure of complexity called algorithmic complexity, the shortest algorithm needed to generate an object. Objects that only require a short algorithm to fully generate them are considered less complex, and vice versa. Gregory Chaitin is one of the pioneers who set the mathematical basis for this field, including the mathematical definition of algorithmic complexity back when he was a teenager. He went on to develop this field with groundbreaking work that is now included in fundamental textbooks of mathematics, computation science, and complexity theory. And this includes his work on Gödel's incompleteness theorems and algorithmic randomness, as well as the omega constant, also known as, you guessed it, Chaitin's constant, which has shed light on the limits of mathematical knowledge and computation. It is one of the deepest mysteries known to the human intellect. In our discussion, we'll touch on a wide range of other topics, including the foundations of mathematics, the philosophy of science, the nature of randomness, and the implications of the new developments in artificial intelligence. We'll also delve into the concept of transdisciplinarity, the idea of breaking down barriers between different fields of study to gain deeper insights into complex problems. It was a real honor to moderate this conversation, including the Q&A session with academics, researchers, and curious people from the UM6PU community. It was a unique opportunity to hear directly from two brilliant minds as they reflect on their life's work and share their perspectives on some of the most fundamental questions in science and philosophy. I hope you find this discussion as illuminating and thought-provoking as I did. My main channel is in Moroccan Arabic, and this English channel is actually still in its infancy. So to support it, please consider subscribing. I would really appreciate it, as it is very important for the YouTube algorithm and the way this content is shown to other viewers. Let's try to reach the 4,200 subscribers mark so we can invite more quality guests who help unlock the meaning of life, the universe, and everything. Dear viewers and listeners, Gregory and Virginia Chaitin. So we will do two journeys in this 1 hour that we have together. The first journey is going to be the Chaitin's journey, and then we will move to the work, and we will try to simplify and make some of the concepts that you're interested in more accessible to the audience. So I had like a long file with another huge introduction for the Chaitins. Already I covered a lot of ground, but what I wanted to do is that you guys introduce each other. So, so my first question to you is, can you please introduce us? Introduce Virginia to us, and also what is the most impressive thing about Virginia, both at an academic level and a personal level, and then she will do the same.
My goodness. Okay. Well,
you thought it was going to be easy?
Yeah. Well, we met at a scientific meeting in Rio de Janeiro, and we had lunch together with a mutual friend who invited the two of us, and the topic was very philosophical, right? And that's how our romance started. I've worked in foundations of mathematics all my life. Virginia has many interests. She has many interests. She's done many things. She's much more versatile than I am. And maybe she's more courageous also, that she just drops a field and goes to another field. And my great good fortune in life was meeting Virginia, and that she was willing to marry me. And amazingly enough, at the age of 70, I had my first child. Virginia gave birth to our son, who's now 6, and then our little girl, who is now 4. So I feel very fortunate, I thank God, for having that wonderful experience of having children, which I didn't expect to have that opportunity anymore in life. So,
so what are some of her research? So that's amazing, that's overwhelming, that's very heartwarming. And what about her academic?
Well, both of us, as we found out very quickly chatting together, both of us got into philosophy through Karl Popper, The Logic of Scientific Discovery, who is a philosopher who writes almost as if he were a physicist. So for me, it's very easy to understand. I don't understand Deleuze, for example, or the kind of people that Virginia understands. But Popper is a good entree because he speaks the language of a physicist. So we started chatting about that, and Virginia is unusual that she lives her philosophy. She believes that philosophy doesn't just have to do with writing papers, but you should apply it to your own life, which I thought was remarkable. We have collaborated on a lot of interesting topics, principally metabiology, which is a little embryonic field that I tried to create, where we really worked together quite closely on that. And I would say that Virginia was my inspiration. Strangely enough, the idea for metabiology occurred to me, I think it was 2 weeks before we got married. So I thank you very much, Virginia. I had reached a point where I didn't think I would have any new good ideas, but thanks to you, it happened, and then we worked together on metabiology. So that's a little bit like having one's first child at 70. It was I was already in one's 60s, and mathematicians don't generally expect to have new ideas. They may have wonderful technique already from a lifetime of experience, but they don't expect to have a basic new idea at the age where I did this, where we did this together. And actually, I could have kicked myself because in some ways I could have done it many years before, but was lacking was the inspiration. So I'm very grateful to Virginia for taking this new subject that I've proposed seriously. Most people don't. So anyway, maybe I've said too much already.
Never. You would never have said too much.
Okay.
Because I've read her works and some of her works, and it's impressive. And so whenever I meet, whether the videos I've seen of you guys or the few moments I spent with you guys, you're in a constant exploration together, of ideas, exchanging ideas. So that's very heartwarming to see. But I want to ask you, the next question, after you introduce Gregory, I want to ask you, how is it like to collaborate as a husband and wife on academic topics? So is it like you say, honey, there's no milk in the fridge. Oh, by the way, I found a new demonstration of the Gödel theorem. What do you think about it?
Well, Virginia originally wanted to be a physicist. So did I, actually. So that was something we had in common. Virginia studied then statistics because she thought it had more connection with the human condition. And my work has been in a kind of a version of probability theory. So we have a lot of points of contact, and both of us, I have always thought in an interdisciplinary way without realizing what I was doing. But Virginia has done a profound analysis of this kind of intellectual developments. So it was a very good match. And Virginia has tried to teach me philosophy that she knows, infinitely more than I do. I'm an amateur. I try to do philosophy of mathematics, but Virginia is a real philosopher. So I'm grateful for the tutoring. I don't know if I've learned as much as I should have. So anyway,
Okay.
Thanks for asking.
Yeah. So on to you, Virginia. Who is Gregory? A husband and then a mathematician and a legend of mathematics.
I'm not sure I separate Greg like this. I find it like very mysterious that Greg and I met. Very mysterious, because there are so many aspects in which we sort of individually led our lives until the moment when we met. And so so many previous experiences led us to actually be able to stay together, right? So first of all, I would like to say that it's gratitude, thankfulness, happiness. It's like a sensation of being in tune with the movements of the universe, let's say. Okay, now, who is Greg? Greg, I have written a preface? No, a foreword for a book paying homage to Greg. And I remember when I first saw him in this meeting that he mentioned. And I had already read some of his work. I had cited some of his work in my work. And I thought that he was, like an older gentleman. And when I see him speaking, and this happens today, it happened this morning, he's an adolescent. For the good, the bad, and the ugly. Greg is an adolescent. And, oh, well, how awful, he is immature. Well, what I can say is that it is challenging, it is interesting, and it is, I don't want to use the word rewarding, but it's alive, to interact, to be married, to work with, to live, to share, to teach, to learn, to go around this path of life. I like to be married to you.
Thank you. Great. Well, good.
Yeah, okay. So he is like an adolescent. Mathematician, yes, but mostly I think that Greg is an artist. Yes, mathematics has this aspect of taking beauty into account as an epistemic value for math, for a beautiful theorem, a beautiful demonstration, the beauty of the mathematical world. But Greg's math and Greg's, let's say, artistic vein is not that of law and order. It's not of law and order. It's of the, it's creative. It's creative in the sense of something that is really violently different from what already exists. It's violent. Something that is, to me, unsettling many times. Unsettling, but wonderful, wonderful, wonderful. So, Greg is a mathematician, an artist, more an artist than a mathematician. His art is unsettling. It's sometimes a bit violent, but it comes written in mathematical language. It has a connection with precision. It has a connection with a certain definition of a conclusion that has to be drawn from premises and that has to follow a certain reasoning. So it's a very Dionysian force, but it is written in a Napoleonian form. Right? So it's contradictory. Greg is contradictory. And it's rich.
Yeah, so it's almost like that destructive power that is not, that, like, you get in order out of chaos. So you first need to shatter the establishment, and then so that you can build something out of it. Is it in a way?
You know what it is? It's not that you get order out of chaos. I wouldn't say that. I would say that you express chaos in an orderly fashion. And that is the
Right.
beauty of it, because it seems like it's impossible. So it is, you know, you go around this impossibility.
Right.
I find it very poetic.
It is. It definitely is. Okay.
Virginia is truly remarkable, as you've just heard her. Her analysis is just spectacular.
Yeah, it's actually also from our previous conversation, we discussed a little bit about arts, you know, religion, different traditions around the world, the history of you know, Islam and so on, and actually. In a way, when we wake up as minds, we wake up in the universe, and we are struck with it. What is this? Like, we spend our lifetime as minds trying to figure it out. And then there are, you know, there are different traditions that are built to try to understand this, to try to understand the universe. And people then, it becomes a sociology of trying to understand the universe, and then people put labels on them. Let's call this mathematics, let's call this biology, let's call this art. But at the end of the day, it's a mind that is trying to explore, as if exploring is a nature of the mind, in the nature of the mind to explore and to try to figure out what is this, what is the world, what are we doing here. And I think you worked a lot on this concept of transdisciplinarity. So tell us a little bit more about that. What does it mean in terms of sociology of science, but also in terms of some of the methodologies that you have suggested in terms of how these different disciplines that have been built throughout the ages can now try to, you know, go back to that foundation, what I said, like waking up to the universe, and without any preconceptions about it and how to explore it, and then just go back to that raw state of trying to figure out the world. So what are your works in terms of, and maybe a simpler, just a gateway question, which is just in terms of terms. So there's transdisciplinarity, there's interdisciplinarities. What are the differences between the two? How does it work?
Okay, so let's begin by the end, right? Which is like trying to understand the terminology around departing from the disciplinary view, where subjects were divided and well defined into disciplines, as if like math, chemistry, the arts, sociology, anthropology, history were individual and separate forms of the search for understanding. Okay, so when we realize that this does not really apply when one is researching, or when one is facing a real world problem, or when one is facing this quest for understanding that you mentioned, you can start by just saying, well, I'm going to try to understand whatever it is that I'm interested in, using first a mathematical background, then a historical, then through art, then through sociology, anthropology. That is multidisciplinary. Interdisciplinary is when I try to look at a question or the problem, making an interaction between these different points of view. Transdisciplinary is when this interaction, builds on itself and emerges something different from what you were considering. For example, you were looking at something using, let's say, math, biology, and chemistry. And suddenly, a new vision arises that is not anymore the connection between math and biology and chemistry and math, but it is a new transdisciplinary point of view. And then there is also cross-disciplinarity. When you, whatever you are studying or whatever problem you are solving, you also call in the stakeholders. You call in people from outside the academic world, or you call people from outside the business or the enterprise, like, for example, if you are building a great compound like the one we are in, and you also ask people that live around here, what do they think about it? So that is already a cross-disciplinary move. So this is just a classification so that we take into account how widely this movement has gone in society, in the academic world, in the business world, but at the same time, it's still so difficult to practice because people stick to their own disciplinary education or to the tag that they have as an engineer, a philosopher, a writer, whatever. So this has to do, I think, a lot with building identities.
Look, and go ahead.
Yeah, but those silos are really an opportunity for the researcher, because if people are stuck in their disciplines, then between the disciplines, in those gaps between disciplines, that's where opportunity lies. That's where maybe people haven't explored. So for the adventurous, it may be
an opportunity.
Yeah, it may give you trouble as a career, for example, but there's a lot of opportunity in those gaps between different fields where people are not straying.
Yeah, well, the silos were built for a reason, actually. They're very efficient in their own right, because that they help build a certain language to get to a more perfect understanding of that specific phenomena. But if you want to really deeply understand the world, you need to go back to that, what I was saying, like waking up and saying, what is this, without any presuppositions, and that can only happen if you shatter all these traditions and all that, those norms, which is what you do, which is amazing. Let's.
I try to do.
We will get to the bit of the biology, which is actually a clear textbook example of transdisciplinarity. But I want to dive a little bit with you, Greg, into some of the key groundbreaking research that you have been involved with, which is algorithmic information theory, right? So I have read you describe algorithmic information theory as taking Alan Turing's work on computation and taking Claude Shannon's work on information theory, putting them in a cocktail mixer, shaking the whole thing, and then you get that. So tell us a little bit about that. What is it? What is algorithmic information theory? And also the ingredients. So we can actually just do a little bit of popular mathematics or popular information theory. What is Turing's work? What is Shannon's work? In very brief terms, because we can spend hours on this, but just to lay the ground for audiences from different backgrounds to get a feeling of of how it works.
Maybe we could mention Gödel, because an event that wrecked my life or changed my life was at 11 years of age in 1958. There was a little book published called Gödel's Proof. And I read it. I was 11, and I was fascinated. And it sort of took over my life, the attempt to try to understand better the incompleteness phenomena in Gödel's proof. And my way of understanding it was to find a completely new framework, a different way of looking at it based on completely different methods. And I was looking for ideas everywhere. You know, I read a lot. As a high school student, I could use the Columbia University libraries, even the stacks. As a child, they let me use the adult section of the New York City Public Library, which was very good then. And I had piles of books like this. And what I was good at was I usually didn't read a book from cover to cover, but I was very good at finding a basic idea. I could filter it out. You know, a lot of books didn't have any basic ideas, really. Textbooks, for example, I hated. But so I was looking for ideas, and Shannon's information theory I thought was very interesting. It was relatively new at the time. There was an article in Scientific American that had been published, I don't know when, sometime in the 50s, by Shannon and Weaver. Weaver was a research administrator who sort of discovered Shannon and helped to popularize him and support him. And the computer was a new idea then, and I felt that the mathematical possibilities were enormous, that it was more than a practical technology. It would lead to a new mathematics, and it would lead to a new approach to philosophy.
But the original work of Turing was actually very philosophical. He wanted to understand the nature of knowledge.
Yes, it had to do with a problem proposed by Hilbert of formalizing mathematics, of showing that mathematics give absolute certainty.
Yeah.
Hilbert was a famous mathematician. And, you know, in a way, Turing, you could say, simplifying enormously the actual history, which is complicated, that Turing invented the computer in an attempt to resolve a question about the philosophy of mathematics. Yeah. So that was an indirect consequence of a philosophical quest. So I felt that the computer was, you know, a completely new philosophical tool, idea.
Yeah, so just off the record, all this, you know, all the computers, the modern life, the entire modern life, which is deeply digital, is based on someone who's like laying down and looking at the sky and trying to figure out mathematics.
Right, and another crucial person was John von Neumann, who was also a student. Well, he was directly a student of Hilbert's. Turing wasn't. And he did more than anybody else to actually create computer technology in the United States during the Second World War and immediately afterwards. So these were two mathematicians whose original motivation was deeply philosophical. In spite of the fact that Turing was English and continental philosophers don't see eye to eye with English philosophers, but still, Turing was taking Hilbert seriously, who was a German, and it was a very Germanic approach, Hilbert's, to the foundations of mathematics. So, why am I saying all of this?
Turing and then Shannon and then...
Yeah. Now, Shannon was another new idea, so I kept looking for new ideas. And I sort of started connecting these three thinkers, Gödel, Turing, and Shannon, and playing with the ideas and seeing new combinations. And it occurred to me...
So
yes.
Turing is about computation.
Right.
And Shannon is about information. So can you just...
Measuring information, the bit. Although you can trace it back to Leibniz, you know, bits should be called Leibnizes, actually, 300 years ago. Mm-hmm. But Turing, Shannon was certainly somebody who was important in creating this notion of information. So these were new ideas, and it occurred to me that you know, Shannon's theory was a statistical theory where you talk about average, you look at a whole ensemble of possible messages and how, when you actually receive one message, how much information does that give you? So this was a very much an ensemble statistical approach. And it occurred to me that using Turing's idea, you could have a completely different approach where you would look at an individual string of zeros and ones and ask how much information there was in it. And the way it occurred to me to define that was to say, well, the best possible compression of that as an individual string. You're not thinking about an ensemble of all possible messages and statistics. Is just to ask, what is the shortest computer program that calculates that message, that string of zeros and ones? And that is a measure of the algorithmic information content of that individual message. So you're looking at individual messages, not at statistical ensembles of messages, as in Shannon's approach.
Right.
You see?
So we are in a library here. So Shannon's approach would be to take all these books and then do statistics on them. So
Absolutely.
What's the frequency of the letter E or of the word the or whatever, and quantify that. Do the math of it. But the approach you're talking about is just take one page and then
One book.
And then think of the question: what would it take to generate this book, or what algorithm?
It's a digital object, and what is the best compression? Well, the best compression would be the smallest program. The way you compress a message in algorithmic information theory is different from the way you compress it in Shannon's more useful, more practical approach.
Yeah.
Communications theory in the presence of noise, typically. You add redundancy to eliminate noise. But with the clearly it seemed to me that the best possible decoder would be a universal computer. So the best possible compression would be the shortest program, and you send that across the channel. I didn't care about noise, although as a practical engineer, Shannon did. He worked for Bell Labs, and that was very important for the telephone company. But I was doing philosophy, right? So, and then when you get the message at the other end, you put it in a computer and you calculate. This is like rehydrating freeze-dried food that you take up into the Atlas Mountains, you know. You melt snow and add that to the dehydrated food, and you get back something you can eat. So this was the idea of...
But your idea of compression is
one individual message.
Yeah.
I'm not
Yeah.
looking at an ensemble of possible messages.
So the analogy here would be, if we have a book, for example, in which there is just the letter A repeated 1,000 times, the compression would be write A 1,000 times, and then you send it through the channel, and then you decompress it into the book.
Right, or write A 1,000,000 times.
Yeah.
Or the digits of pi look very random, but there are concise programs to calculate it. So instead of giving digit by digit, this would be a long message if you wanted to give the first 1,000,000 digits of pi. You send a program for calculating pi, which is relatively concise, and then you run the calculation at the other end. But the most interesting thing philosophically is, Shannon information theory is practical engineering in a way. And I can sell these ideas that way, but I prefer to think about them as philosophy of science. And what you think about is that the message is not a message. What it is your data. You've done an experiment on a physical system, and you get a series of bits, right, your empirical data. And then you look for a theory. What is a theory for this experimental data? Well, a theory would be the most concise program that generates your empirical data. And if there is no concise program, then the data is unstructured, it's lawless, there is no theory. And this is an idea that can actually be traced back to Leibniz's Discours de métaphysique in 1686. You can go to the Gallica website of the Bibliothèque Nationale de France and get the first published version of the Discours, which was only around the year 1900. This was a document that was in the Leibniz Nachlass, or whatever it is in German. Leibniz left, I don't know if it was 100,000 pages of notes and letters, and people kept looking for stuff, with his bad handwriting, and he would write notes in the margin and notes on the notes in the margin, and to get this into a text that can be published is, a non-trivial undertaking. So someone found a text that a scholar whose name escapes me, who gave it the name Discours de métaphysique, but it had never been published. Leibniz didn't even send it in a letter. He sent a summary of it to Legrand. What was the name of this, this Frenchman, the philosopher? He was a Jansenist theologian, and it was just the topics of the different sections of the Discours, and the reply was horror. that it was heretical. So Leibniz never sent him the complete text and never sent it to anybody, but it stayed there and was found hundreds of years after Leibniz's death. And then, and it was Hermann Weyl, who, by the way, who discovered this, a student, maybe some people say the best student of David Hilbert. John von Neumann was also a remarkable student of David Hilbert's. It was Hermann Weyl who noticed the significance of these remarks in the Discours de Métaphysique. And I was not a Leibniz scholar by any means until I read some philosophical works of philosophy of science by Hermann Weyl, where he refers to the Discours de Métaphysique. But it was hard to track down because they had translated the title of the Discours into German and from the German into English, so it was unrecognizable. And then I found another work by Hermann Weyl where, Discourse on Metaphysics, it was translated from the French to the English, so that gave me a start into. And by the way, Gödel was totally mad about Leibniz. He was obsessed with Leibniz, and I thought it was a sign that he was clearly mad. However, having studied Leibniz myself, I think that Gödel was right. Leibniz is fascinating, absolutely fascinating.
So in our example of the book, so if it's 1 million times A, we don't care if it's 1,000 books of 1,000 A's each, because we can always compress it into this computational algorithm that can generate it. What if the book has just random, I'm not, the word is loaded, but if it just has a random sequence of letters, would
then it can't be compressed. It can't be compressed. So the shortest message is basically to have a program that says, just print this out and give each. So that would be a series of observations, if we're talking philosophy of science, which I prefer, a series of observations that have no structure, for which there is no law. Because anything you can get from a computer program the same size as what you're calculating. There's always a theory the same size. This is a remark that Weyl noticed that Leibniz sort of made. And Weyl made it sharper. Hermann Weyl made it sharper. The way Hermann Weyl put it, if you allow arbitrarily complex laws, the concept of law becomes meaningless because there's always a law. That's Hermann Weyl's improvement of the original statement by Leibniz. Which was during a snowstorm, by the way. Leibniz was consulting for the Duke, trying to improve the output from a silver mine in the Harz Mountains. And of course, the miners were not very pleased to have a philosopher getting involved. And there was a bad snowstorm. And so to while the time, Leibniz composed the Discours de Métaphysique, which among other things contains, I think, the first statement of the conservation of kinetic energy? Vis viva, I think Leibniz called it. He discusses an elastic collision, I think. And this is something that Newton did not come up with. So it's a remarkable work. Leibniz is amazing.
It's a legend.
Yeah.
So what are some, while doing algorithmic in information theory, what are some of the most profound realizations that you found in terms of that had epistemic consequences?
Right. So I view this as philosophy of science, right? It's like a toy model of what physics is all about, right? So a theory, the empirical data, you simplify it to be a finite string of zeros and ones, and your theory is a program that calculates it exactly. And then the smaller the program, the better the theory. And if the smallest program is the same size as your observations in bits, there's no theory, it's unstructured. Now, how do you get into interesting epistemic waters? Well, it's very simple. Let's say you have a theory for some empirical data, and you want to show that it's the best theory, that it's the simplest possible program that explains your empirical observations. It has to explain it precisely, by the way. It can't make any errors in this toy model. It can't be a statistical theory. It has to give each bit of the... This is a toy model of real science is obviously much richer and more complicated. So it turns out you can never be sure that you have the best theory, the most concise theory. ever. This is a fundamental limitation of mathematics, it turns out.
Sorry, so what's the realization? So
That you can
given
never...
data,
Yeah,
given
if
this library?
if this is a sort of a toy model saying what the best theory is, it's the most compact, it's the most concise, it's the smallest program that calculates your empirical data. Let's say you have a theory and you wonder, could this be the best theory? Could this be the most concise program that calculates what it calculates? And the answer is you can never prove it. You can never be sure. Well, except in a small number of, as mathematicians like to say, in only a finite number of cases. You know,
Yeah.
they dismiss any finite number of. So it's a fundamental difficulty. This is an incompleteness theorem, completely different in flavor from Gödel's proof.
But so the book that has the A's, the A, that one we can...
Yes. Yeah, pretty much so.
Okay.
Because
So,
it's, yeah.
so the realization is that most books or most possible data structures cannot be reduced to a theory that describes them exactly?
No,
Or,
it can be, but you can never be sure that you
Sure,
have it.
okay.
That's it. Except maybe for very a small number of simple cases where the theory is very concise. You know, you might be able to show that this is the most concise possible theory,
Okay.
like in a billion A's. But even that can get complicated. If the number of A's is a very complicated number, you may not be sure that you have the most concise description of that
Yeah.
number. I mean, there's this,
Yeah.
but you know, so the general idea is here
So-
you have a definition of the best possible theory, but you can never prove it.
Okay. So most possible points of data have no explanation in this sense.
No, they have
theory.
explanation, but you can never be sure you have the best explanation.
never
You
be-
can never prove you have the best explanation.
Okay. Okay. So
This is a fundamental limit on the power of mathematical reasoning.
right.
Ask again if it's not clear.
No, it's clear. So you can find a theory that explains the data, but you cannot be sure it's the...
You may find many theories, and the question is if you have one that you suspect, you know, I mean, what do they call it? A theory of everything?
Yeah.
And physicists would like to find this very simple set of equations that explains the entire physical universe, right? God's
Right.
choices for creating
Yeah.
the world.
Yeah.
So the general idea would be that in general, it might be that you have found, in fact, but you can never be sure. You can never prove it.
You cannot prove it.
Not in general. Maybe for a finite number of cases, which includes our universe, you know, but...
Yeah.
So this becomes then a fundamental result in epistemology about mathematics. But the original motivation was saying, what's a scientific theory? When is it good? You know? But from there, you go immediately to an incompleteness theorem. You see? Big surprise. Ideas are all connected. You see? So this is a completely different approach from Gödel's approach. You know, the famous, I mentioned Hermann Weyl. When Gödel published his incompleteness result, which astonished me when I was 11, Weyl was so upset that for 1 year he couldn't do any math research because it pulled the rug out from under his conception of mathematics that he thought gave absolute certainty. And I mean, he eventually overcame it. The way you overcome it is, like any disagreeable topic, is you don't think about it anymore and you just keep going, right? But our view is that mathematics, this is actually good, not bad. What this means is that mathematics is an open and endlessly creative system. If Hilbert had been right, mathematics would be a cemetery. You would have certainty, but it would be the cemetery of the grave.
So Hilbert was trying to find an axiomatic theory of everything. In the sense, you have a set of axioms, and you can derive all truths.
All mathematical truths.
all
A theory of everything for all of math.
And that failed. That project failed.
That project failed brilliantly because it led to the creation of the computer industry as a minor
spin-off.
minor spin-off. Yes, but Gödel already exploded it in 1931, and Turing did it in a different way with the halting problem in 1936. And I've been trying to do it using notions from information with a completely different approach. And you see, part of the problem is the way Gödel did it. He has an assertion, a mathematical assertion that says of itself, I'm unprovable. So that means it's true if and only if it's unprovable. So that shows there's a limitation, but it's a very strange, in mathematics normally you don't see assertions which refer to themselves and say I'm unprovable, right? So that's a very strange assertion. So the question is, do you have to take Gödel seriously? If you take Gödel very seriously, you may give up on proofs, and just adopt an empirical attitude to mathematics, which would be unfortunate, But the question is, how serious is the incompleteness phenomenon? Does it only apply to very bizarre mathematical statements that you could construct explicitly in order to show that there are limitations? Should you do mathematics differently as a result? And the math community decided to shrug it off after initial terrible shock. Fortunately, I don't think anyone committed suicide, but a year of mathematics that Hermann Weyl could have done is a loss to mathematics, because he was a wonderful mathematician. So the question is, how seriously should you take it? So what I did is I bet my life, maybe I got it wrong, on the idea that incompleteness was significant and meant that mathematics was different from what people thought. In fact, I'm a backer of what Imre Lakatos called a quasi-empirical view of math, which means that math is not an empirical science, it's not physics, but maybe it's not as different from physics as people think. So that's my personal take on what this means. But I could be wrong, and I may just have spent my life betting that incompleteness was important, and the math community has decided that it's not. They decided to go ahead, not lose faith. It's a religion that mathematics gives absolute certainty, even after Gödel. They say, oh, well, in practice it doesn't make any difference because the kind of things we want to prove as working mathematicians are not instances of something that's true but unprovable. That's the faith. I can't go against people's religion. If that's your motivation for doing mathematics, that this is a pure, perfect world, it was part of my motivation as a teenager, they may be right,
but at least you can prove some things.
A lot of things can be proved. Mathematics has advanced enormously since Gödel's incompleteness.
But your view is that it's a creative process. So you just pick up a set of axioms, you go and explore what they give, but you don't have the certainty that you can know everything that is knowable.
You have to expand the principles you're using. It has to grow. It's creative. It's an open system. I've been trying to make arguments for that using information notions, from algorithmic information theory. Now, I don't know if I've convinced anybody, but I've done my best to be provocative and I've tried to open the door at least. Mathematicians go on as before. In general, they don't like philosophy. Mathematicians, they want to do mathematics. They want to prove important results. Hilbert is from the German-speaking world at a time when the Germans have a very strong philosophical tradition, and it was even stronger a century ago, more than a century ago actually. So he asked a profound question and got an interesting answer that he was wrong, but you invent computer technology as it was a very good question.
Yeah, absolutely.
He made a very sharp question out of what seemed like a mushy philosophical issue. He made a question that could be attacked mathematically, you see, which Gödel did and then Turing did with a different toolkit, and then I've done with a yet different toolkit. But I think the issue is still open, of how seriously one should take incompleteness. Gödel himself, by the way, has essays. I've written a little book on this at the IAS, and you can download it from my academia website. If you Google Chaitin Academia, you get my academia website, and the first thing on it is a book called Philosophical Mathematics, Infinity, Incompleteness, Irreducibility, which is a little 68 book with a lot of illustrations that I was privileged to be able to write in the IAS. And there I have extensive quotes from Gödel, where Gödel actually does express what I think it's very clearly a quasi-empirical view of mathematics. You know, so, but you know, I don't know if we've convinced anybody, but we've tried at least to raise the issue as sharply as possible, you know.
Right. So let me ask you one question that you very quickly went through earlier. I think it deserves way more time than what we're going to give it, but let's give it 5 minutes. Okay. And then we do metabiology, and then we open the floor for the question. So the question is a very profound one, which is the nature of existence. So it's what philosophers like to call this the ontology. So what is what is existence made of? And if you ask most physicists, they will say there's a physical world. It's there. We can model it with mathematics, but it's not mathematics. It has a physical, at least many of them at least say so. But there is another point of view which goes way back to Pythagoras, which is the point of view that it is actually made of mathematics and nothing but mathematics at the foundation level.
Yeah, well, God, you know, what tools does God use to create the universe? You know, you don't make it from marshmallows, right? You know, mathematics is something very clear and sharp. I don't agree with this modern view that fundamental physics doesn't try to find the fundamental nature of reality. You're just making models that apply in different areas. This is the more modern, modest approach. You know, I'm a romantic. I was a student a long time ago when people still believed that physics could find the fundamental reality. And following Leibniz and the computer, I believe that God is not a pure mathematician. Well, he sort of is. But I believe that instead of building, you know, what is it? All is number, God is a mathematician. I like to say all is algorithm, God is a programmer. You know, so this is digital philosophy, this is called, that the world is built out of information, out of zeros and ones. That's a possibility. You know, who knows? I mean, the world has a right, or God has a right to decide, right?
Don't tell God what to be.
Yeah, we're doing pre-Socratic philosophy here, you know, the speculation. Everything is fire, everything is one, everything is flowing. So this is an attempt to use pure thought.
Right.
So
my question to, not you, but to those who say there's a physical, special thing that gives physical or mathematical structures a physical existence, my question to them is, so this is a bottle of water, you can model it, at least in quantum physics, in the fundamental theories of physics, entirely with mathematical structures, whether it's a wave
very
function.
Very complicated mathematics.
Very complicated.
Quantum mechanics.
But my question to people who say there's a physical reality to this bubble is, what else is there? What else, additional to the very complex mathematical structures, do you have to breathe something into these equations so that they become a bubble? If yes, what is that thing? That's my... Well, I've never heard an answer to this question.
Well, that would be God's choice, of which... This is discussed by Leibniz, by the way, in the same Discours de Métaphysique. You know, what he says is that God has created the best of all possible worlds in the sophisticated sense that the hypotheses that he uses to create the world are minimized, and he's simultaneously maximizing the richness and diversity of the world that these hypotheses, which I think Leibniz was thinking were mathematical hypotheses, create. Now this is, by the way, Leibniz's attempt to show that theism is compatible with the mechanical philosophy, which we now call science. You see, so as an attribute of the perfection of God, the world is comprehensible, because the universe is a great work of art that is built from few bricks, you see. So Leibniz thought that atheism, I believe in some letters, he says that the French philosophers were pretending, like Descartes, were pretending not to be atheists, but they had to escape from France because it was pretty clear that they were sympathetic to that. And Leibniz thought that atheism would be destructive for Europe, which I think is an interesting question.
Yeah.
So Leibniz always tried to show that things were compatible, that people thought were incompatible. He made an attempt to reunify Protestantism with Catholicism. Of course, he did not succeed, but it shows his philosophical temper. So he wanted to show that theism was not incompatible with science.
Yeah,
what we call
but
modern
then
science.
depends also, theism, there is theos, then how do you define theos? What is the definition of God in this case?
Right.
The one that makes contingent things be actual. In this philosophical sense, is very different from other types of other definitions of God. But at least,
right.
My question, even for that view that there is something, you call it God or you call it whatever you want, that gives an actuality to a contingent or to a possible universe. Then what is the nature of that as well? Is it?
Well,
unless you hold the view that everything that is contingent is also actual, in which case it's very easy. Then
no,
everything
I don't believe in the multiverse. I think that's a cop-out in modern physics to say that we don't care about the laws of this particular universe, where you study the ensemble of all possible universes, the multiverse.
Yeah.
Well, that says I don't care about empirical science anymore. You know, I don't like that. But, you know, so we have one universe, and if you're saying we cannot know, I guess Kant said that, we cannot know the fundamental nature of reality, we just see things indirectly. Okay, that's a possible view, but I'm a romantic. I think that fundamental physics, you know, people like Einstein and Schrödinger were not just building models. They thought they were trying to probe the fundamental nature of reality. Now, Einstein was very modest about it at the end of his life. He said, well, maybe everything I worked on was a mistake, you know. I'd like to understand what the electron is, he said. So it's always tentative, but I think there has to be some ontological basis. You know, I think you're giving up if you say, we will never know. I don't. Leibniz also was not an agnostic. He thought that God could be understood through reason, even though God is infinite and we're finite. So I'm a romantic. I think that the universe is built out of something. And in principle, I think we should try, and we might succeed in knowing, or we might never. But I think one has to try.
Yeah.
You know, and I think saying that there is no ontological basis, that it's all, I don't know, marshmallows down there, is giving up. You know, I think this quest for fundamental understanding is beautiful and honors the human mind.
Yes. And that exploration power that we're touching on. Virginia, what do you want to share your thoughts on this topic before moving to the metabiology question?
Yes, well, you see, Greg just mentioned Kant on him saying that we cannot through reason know the noumenon, which is what we call the ultimate reality. Kant was in some ways expressing what he thought were the limits of reason, which are in some way, I wouldn't say analogous, because analogy is too strict a comparison, but they can metaphorically connect to the limits of mathematics or of mathematical reasoning. So when Kant writes the prolegomena to any future metaphysics, it was understood by most that what he was saying is that metaphysics is a theme, ontology, metaphysics understood as ontology, as something that you cannot really investigate because it's beyond reason. But one can also interpret what he was saying is that you have to use a different form of approaching that is not really rational reasoning, right? So this is just a little reminder that the fact that you cannot, through reasoning, achieve maybe an understanding of ultimate reality, that doesn't mean that you cannot use other pathways. And, well, you see, I believe in different forms of knowledge that are not only scientific. I believe in different form of using the human capacity for thinking, reasoning, perceiving, organizing our experience, and conducting our intellectual, let's call them powers, or intellectual capabilities. And getting back to your question, I do agree with Greg that we should not give up and just say that, well, everything are just attempts to understanding, and that the only thing we can do is like build models that give us approximate grasp of what's going on, and we should use them instrumentally for our purposes, which are to survive, to solve our problems, our everyday lives. I think that would be a little too shallow if you go back to what you were mentioning, which is the everlasting quest for understanding that humans have been showing they have. They're not always dedicated to that because we have, we have to survive. We sometimes don't have the chance, the opportunity to, step back and think about these beautiful topics that are more existential, that are deeper, but still we shouldn't give up on them.
Right. And science and also mathematics have continuously shed the light on these foundational questions. For example, one thing that struck me was I was watching a conference by Leonard Susskind. He works on the foundation of physics, which is an empirical science. They only care about empirical results and so on. And at some point, he was mentioning actually results from your works, Kolmogorov complexity, which is basically what we're...
It's actually my complexity.
It's your complexity, so Chaitin complexity.
The person who actually does something never gets the credit, right?
Yeah. So
C'est la vie.
So it's the idea that we were discussing just now, which is what is the shortest algorithm that can give you. And he was...
Kolmogorov got it wrong.
Right.
Yeah. Three of us came up with... There's also a gentleman called Solomonov, who was a friend of Marvin Minsky, interested in AI. The three of us thought that you should look at the size of programs rather than the time that programs took, which everybody else thought was the key question. And what happened was the original proposals had some flaws. So the idea was sort of okay, but mathematically it was very badly formulated. So 10 years later, I think Kolmogorov was already dead, I redid the definitions, and you got a very beautiful, elegant theory. So it sort of annoys me when people call it Kolmogorov complexity when he never saw it, never wrote the right definition, never wrote the right equations, and I did.
Right. Okay.
But this is how the cookie crumbles, right? You do the research for the pleasure, and the rest is politics, right?
Yeah. Sociology,
so if I had a
politics.
bigger army than Kolmogorov, people would call it Chaitin complexity.
Okay.
But I don't.
Yeah, so I was watching so it was a physics, fundamental physics, and he was talking about black hole. It was talking about the emergence of space-time, and and suddenly he talks about this. He talks about what is the shortest algorithm that can generate a sequence of bits.
Right.
So here you have something that was developed in a completely different motivation, and you found it at the foundation of physics.
I've drunk beer with Lenny Susskind. He's a great guy. Virginia also knows him. We bumped into him in Canada, in Santa Fe, I think it was. He's a great guy, but I think he's a believer in the multiverse. And I think the multiverse is completely pernicious. You know, I think that string theory has been the death of theoretical physics.
Yeah, right. But still...
and he's one of the major string theorists, if I'm not mistaken.
he's one of the founders, but he doesn't call himself a string theorist.
Right.
He's more open.
Right.
He says he's just... I interviewed him, by the way. He's a great guy. He's more open to exploring what we're talking about, exploring.
I think we were both poor kids in New York.
He wrote a book about the string theory landscape, which is exactly
it's the multiverse.
The multiverse.
Yeah, we were having beer one day, reminiscing that we were both poor kids in New York City. I went to the Bronx High School of Science, a magnet school. Maybe he went to Brooklyn Tech or also the Bronx High School of Science. And he was saying when he was a PhD student, they paid no attention to their teachers. You know, they were all rebels. They were going to create a new field. And he's very disappointed in his current students because they come to him and they ask him to give them a problem. And then they just work on it for the rest of their lives, writing one little paper after another on this. You know, so he felt it was sort of disappointing. But those poor students that do that, they're forced to do it by the system now. Doesn't really let you do real research, in my opinion. And this is we were talking to a Nobel Prize winner in biology, one of the creators of molecular biology in Singapore. His name is Sidney Brenner. And he was in a wheelchair, but his mind was, you know, spectacularly sharp. And he said he had a lot of friends who had won Nobel Prizes, you know, creators of molecular biology. And he said none of them could have done the work that gave them the Nobel Prize in the current environment. You know, with the current funding system, the kind of refereeing, with the whole thing. Yeah. And it's a problem. I avoided the system because I was doing engineering work for in an industrial lab, and all this stuff that is the reason I was invited here to the Institute for Advanced Study was my hobby. And at that time, an industrial company would tolerate it if one of their employees spent part of his time on blue sky research. I think now, you know, they want to stamp out anybody wasting their time because the stockholders are going to, you know, have their hide. So the current environment is not as friendly. So I don't know.
A lot of the groundbreaking research from the past century wouldn't be published today because the researcher would spend years not publishing any papers and then come up with the idea.
Yeah, and you can't do that. You can't do that anymore. Yeah. So I think it's very sad, but the bureaucrats want to control what's being done because real science is subversive, and people are scared, you know, because it threatens the economy. It has political consequences. You know, if you come up with a completely new technology, for example. So it's too bad. But I think what's going to happen is that this is an opportunity for Africa, maybe for Morocco, because the Europe and the United States have this immense bureaucracy controlling what people are doing research on, making sure that it's relatively trivial work, you know, epsilon advances in existing stuff. And the result will be that someone who doesn't follow this system will make revolutionary advances, you know. So a country is destroyed by its bureaucracy in the end very often, it seems to me. That was my theory. The bureaucracy was like a cancer that eventually would destroy the body of the poor victim. I hope I'm wrong. But, you know, I think we have a problem, this notion of shut up and calculate that they talk about in physics. Yeah, and also string theory has no interest in experiments. You know, it's some very sophisticated pure math that's very fashionable, you know, in the world of pure math. But I don't think it's physics, really.
Yeah, well, it has been described as a tool, a mathematical tool that has opened, in some occasions, some new insights into the universe, like the holographic principle.
Well, yeah, the holographic principle is interesting, and there's also something connected with information theory, with my area, which is this notion that a physical system only has a finite number of bits, which strangely enough grows as the surface area, not as the volume. Yeah, this is based on black hole thermodynamics.
Yeah. So that was the point I was getting at, which is we find in various different areas of science a theme that comes back, which is information. And we find it in the foundation of physics, we find it in computer science, and people want to explore what is the nature of intelligence.
Right, quantum information theory now, the attempt to get space and time not as something fundamental, but coming out from qubit entanglement as an emergent property. So a lot of us find the notion of information an inspiring one in different areas. Certainly, molecular biology is based on biological information, which is DNA, and computer technology. So that's why some of us say, hey, maybe the universe is built out of information at some fundamental level. And maybe it isn't.
Yeah.
This is just a speculation.
Yeah. Great. Okay. Well, I think we ran out of time, which was expected. So what we can do is we can open the floor to questions from the audience, and then instead of half an hour, maybe we can do 15 minutes. So the floor is yours if you have any questions.
And we missed metabiology, but Virginia did a nice interview with Nicholas for the chair of complexities and humanities. A 1-hour interview where she talks about metabiology. If you're interested in that topic.
In which is that in the YouTube channel of the chair, right? So you can go.
And on the website.
And on the website. CCH.
CCH.um6p.ma.
Here you go. CCH.um6p.ma, and you can find that fascinating interview about metabiology, which is another 1 hour of discussion. Okay. Yeah. First question. We have it. Okay.
Yeah, hi, thank you so much for that discussion. I was really interested, after you described your incompleteness theorem as being the idea that you can always have an algorithm that can compress any amount of information, and you can obviously show that an algorithm B is better than an algorithm A, but you can never prove that there might not be a future algorithm C that can improve on that algorithm B. And I was thinking, well, this sounds to me very much like science. Scientific models that improve on past scientific models, but you can't necessarily know that there might not be a better scientific model in the future. But you seem to sort of poo-poo that a little bit, or maybe I misunderstood, when you were talking about the idea that science or physics shouldn't just be about incrementally improving models, but that there should be an attempt to find the fundamental.
I see that as a separate issue. I didn't mean to poo-poo. Your summary of my incompleteness result was right on target. But what I did, I'm a romantic. I would like to find the fundamental laws, and I'd like to understand what the universe is built on. What is the fundamental ontology? Now, whether the human beings will ever know, who knows? But it's become popular to say that theoretical physics doesn't really search for the fundamental reality, that all you do is have models, each model with a limited area of applicability, and then you make a mosaic of many models which sort of cover, like a patchwork quilt, more and more, but that you're not searching for fundamental understanding. Well, that's an epistemological position that I think is too modest, in my opinion. It's sort of giving up on the idea of the search for fundamental understanding in science and saying we're just, what is it, instrumental, you say? I think that's too bad. Now,
but maybe that's how the universe is made of areas that can only be described with patches of theories.
Well, then there wouldn't be one God. Aren't we in a monotheistic country? You would have many gods, and each one has their little fiefdom where they've put other, different laws.
So earlier I said, don't tell God not what to be. So maybe it's don't tell God not what to be or not to be. We don't know. How do I know?
If I may, so I agree with you that the idea that that saying that we can't try and connect theories and connect ideas, and that we should be restricted to a patchwork of mosaics does seem rather modest. But it seems to me that if there was an equivalent incompleteness theory for the universe, in the sense that you could never prove, no matter how good your model, or no matter how good your theory, rather, no matter how good your physical theory, you could never prove that it was the ultimate truth, I think that there is something that could be quite romantic about that, in the same way that I think Gödel's incompleteness theory is romantic. The search is always happening. You are always searching for a higher theory, and you'll never know if you reached it.
Do an
Okay.
comparison to find the best code.
Okay, I think John Barrow would have agreed with you, my late colleague John Barrow. But by the way, what's your area?
I'm an anthropologist.
Okay. You sounded like a physicist. Well, you're doing anthropology of the physics community.
Possibly. I do a lot of statistics, and so I do think about information theory.
Here you go.
That's sort of my angle into that. And I'm very interested in physics, but fundamentally I'm a social scientist.
Yeah, well, I'm very interested in physics, but fundamentally I'm a mathematician. So.
Right.
Yes, question? Next to you, yeah, just, and then we go there.
Hello, thank you all. I think I used to call myself mathematician because I studied mathematics in high school, but that's forgot in front of these minds. My question, I think I believe you have witnessed from the start of the digital transformation from the computer until now, and you have worked on it. And what do you think would be the future of computing with the rise of AI? And what role could you as scientists and your research could play on that? The reason why I'm asking that, I remember we were having a class and we were discussing about IQs, and we realized that AI on chatbots today, they are like 2 times the average IQ or more. And do you think that they would be able to answer some questions that mathematicians are not able to answer, or solve some models? Or how do you see the future of this computing? Where is it going? And what would be our role as humans? And that would be like a question, I think, if you may.
That's a very, very good question. When I was a kid, it seems to me that, well, general relativity and quantum mechanics at that time were the fundamental physics. And the Gödel's incompleteness theorem, there were still people who had really worried about that profoundly when I was reading about this. But nowadays we have a big problem, which is AI. And it looks like it's going to be revolutionary and a technology that has an immense impact. Now, I don't know. You know, your guess is as good as mine. I mean, those of you who are younger than I am will probably live to see amazing things, or maybe not. Maybe it's oversold. You know, it's what a mashup of the World Wide Web, but it's still pretty impressive what it does. So one problem would be, let's say you get this super AI which somehow reads all the experiments in physics and says, oh, obviously, and then it writes 500 equations. You know, these are the fundamental laws of the universe. And we're going to look at it and say, what? These neural nets don't explain to you how they work, right? They come up with something, but it's a black box. So, or if, you know, as a mathematician, I've had some contact with really brilliant people that seem superhuman, in fact. You know, they look like mutant life forms. John von Neumann, who's one of my heroes, people said he was really a Martian, but he had studied human beings carefully and could do a fairly good imitation. Well, it wasn't that good because his wife left him, okay? but still, some of these minds are really remarkable. So these are superhuman human intelligences, right? Ramanujan is another example. So what happens if there's an AI, if there are AIs which are as far beyond our capabilities as we are beyond the, I don't know, the ants, the fourmis in your garden? So even if they came up, they said, oh, I have this wonderful theory of everything for the physical world, and then we couldn't even understand it. You know, it was just too complicated for us. The same way you wouldn't lecture to an ant on, I don't know what, on Goethe's Faust, for example. The poor ant would not be able to comprehend or understand, right? So I think that would be sad. Now, Marvin Minsky, that we interacted with toward the end of his life, he used to like to provoke people. So he would be at MIT saying that we were a carbon-based life form that was creating a silicon-based life form to replace us. And at that time, this was pretty wild. But at this moment in time, I think it's a real preoccupation. I hope I'm wrong. I like human beings. I'm in favor of human beings. I don't think we should try to be robots. I don't know what's going to happen. Another possibility is a symbiosis between artificial intelligences and human beings, combining the best of both, right? So that's another possibility. I mean, you young people, this is your future. You're going to make it happen, right? So I wish I could start over and live to see all of this, but you will. So I think it's an exciting moment. It's a revolutionary moment. It's an exciting moment, and who knows what's going to happen. So it's a very good question, and I don't feel that I have a privileged answer, because neural nets are a new kind of algorithm, right? They're algorithms 2.0, totally different from the kind that I devoted my life to thinking about. And I think that most of my work, as far as I can see, has no relevance to neural nets. I don't know what the right mathematics is for thinking about neural nets. Maybe it's more statistical mechanics kind of stuff. I don't know, This is not my area. So this is an important area for research, I think.
So the worst case scenario probably for the future would be that we kickstart this new form of intelligence, but it's a zombie-like intelligence. It doesn't have that creative power that we do. And if it replaces us, it would be sad for the history of life on Earth. But then there's another possibility, which is we are jump-starting something that is what we were deemed to become anyway. And then we're just a transition phase. So the purpose of life on Earth, or the purpose of our existence, would be to start this new life form so that it replaces us. Maybe.
Well, there are children, there are descendants.
Yeah, exactly.
We helped to birth them.
Yes.
Well, that would be another possibility. I don't know.
Right. Okay.
I like human beings. I don't want the human race to disappear.
Je vais parler en français.
Oui, c'est bien. Lentement, s'il vous plaît.
Très lentement. Mon anglais est trop mauvais. Je voudrais savoir si c'est possible de trouver un algorithme, justement, puisque vous êtes mathématicien, qui permettrait de créer une harmonie incontestable à partir du nombre d'or, le nombre d'or qui a donné une harmonie à l'architecture et qu'on a oublié aujourd'hui. Et que cet algorithme puisse passer à la moulinette tout ce qui se produit en architecture, que ce soit au Maroc ou dans d'autres pays, pour essayer d'éviter les horreurs que nous pouvons voir toute la journée.
Okay, the golden ratio. Well, that has a long history. It certainly leads to harmonious buildings. The stuff we've been talking about...
Pardon, vous avez dit que vous étiez un romantique. Donc la beauté, c'est évident que ça vous intéresse.
Oui,
qu'avoir
bien
votre
sûr.
femme.
Oui, d'accord. But, pardonnez-moi pour parler en anglais. These ideas, I think at least one architect took this measure of program size complexity. You can call it complexity, si vous voulez. I prefer to call it, putting somebody's name on it is always unfair because there are always many people who are involved. I like to call it algorithmic information theory because you see, complexity is a bad word to use actually because it means other things. It's really a measure of information content, I think is the right way. So I've read a beautiful book on architecture, or maybe two, where they were talking about complexity, about the information content of the design of a building. And, how do you say, there's a question of order and there's also a question of surprise. A sphere, a perfect sphere is the simplest possible, or a perfect cube, but it's not very interesting. So there's a tension between simplicity, a concise description of a shape or form, and surprise, right? So music, for example, you don't want it to be completely predictable because that's very tedious music. On the other hand, if you make the maximum surprise by having, how do you say, Gaussian noise, that's totally uninteresting. So there's a tension between order and randomness that is important, I think, in creativity. Now, I mean, the golden ratio certainly has a pedigree going back to ancient Greece, and it's a lovely topic, but you know, I don't know anything about it, to be honest. I don't know if Virginia wants to say something on this topic.
Well, what I could understand is that would there be an algorithm to create architectural projects that would respect the golden ratio? This was what I think she was trying to ask.
Would you want such an algorithm? That's what you were saying, is that you need a balance.
Would you want such an algorithm? Is there such an algorithm?
Let's go to your favorite AI and ask it to design a building based on the golden ratio and see what comes out. I don't know. Taking into account the golden ratio, maybe you have something to say on this topic.
No, no.
Question or comment?
What I would say is that the fun thing about, let's say, this virtual world is that you can do experimentations. You can experiment. You can create your algorithm, create your project based on the golden ratio. You know, and experimentation is something that you can do in the virtual world, which is very interesting and very motivating. So this is a good, I don't know, research project to do this experimentation.
There's actually a deep question related deeply to this conversation, which is beauty. So beauty is extremely complex. You just mentioned the tension between order and surprise, and what it seems is that you cannot reduce beauty to just a one formula. Okay, so one number or one even one short algorithm that would give you beauty. Beauty is extremely. It's part of this creative process that we were talking about. It's another deep question. Maybe we won't have the time to address it. But there was a question over there, I think. Right.
Thank you. A question to Virginia. Do you share Greg's opinion about the multiverse first? And then a common question, which is, so the multiverse is not necessarily related to string theory. I'm not a believer of the multiverse or anything, but I like one observation made on the World Science Festival was that the burden of proof is on the people so because we see one universe, then there is only one universe. And the second, and it is also related to beauty also. How do you see one universe with symmetry and with the notions of symmetry just symmetry, let's say just symmetry. Commutativity, I was going to say associativity, etc.
Okay. Okay. Sure. Yeah. So, if I believe in the multiverse, or if I share Greg's opinion that the multiverse is something that is like physics going a little bit astray.
But sorry, let me just proxy a little bit the question, because when people talk about multiverse, there are actually at least 3 or 4 definition of multiverse. So there is the cosmological multiverse, which comes from inflationary cosmology. So that's physics. There is string theory multiverse, which we have just touched upon. And then there are other more exotic forms of the multiverse. And then there is another even simpler multiverse, which is that's the universe extending way, way beyond the observable universe. That's another thing that some people use the word multiverse for it. So I just wanted to clarify this, and then You tell us what you think. So it's a very loaded term, and it has different definitions.
Right. So, as an epistemologist, I embrace different proposals of different theories, and I do understand what I think I understand of Greg's criticism of string theory is because he believes that physics should have empirical grounding, or at least some expectation of empirical confirmation. And as the history of string theory stands today, it does not seem, it hasn't happened, and it doesn't seem that it can happen, at least we can't visualize this. So this is actually a scientific, let's say, drive, which is that you propose theories, you can use mathematical intuition, and then getting into what you mentioned, which is symmetry. We can think about Paul Dirac, who used the principle of symmetry to create new physics, and he proposed mathematical models that did not have empirical confirmation at the moment, but he proposed them, and that they later did come to be confirmed empirically. But they didn't take as long as string theory is taking. So it all depends on how much patience you might have to wait until a mathematical model, beautiful, mathematically speaking, or respecting this or that criterion, such as symmetry, will actually come to be confirmed. So this is a question of what kind of a position you have relating to that. How long will you wait? But on the other hand, you also, so this is like sort of, let's say, a methodological choice. I will wait for such time. But the history of knowledge and history of science has many interesting episodes. When I think it's in chemistry, you have more than a century before it was confirmed that the atoms, yes, that that atoms exist was centuries. But I'm talking about the atomic weights had to be whole numbers.
Multiples of something. Yeah.
Multiples of something. Yes, that was that. It took. I think it took more than 100 years for that to be confirmed. Yeah. So you see, we don't know. We don't really know.
And even that example of atoms from the ancient Greeks, they had an idea that things are made of atoms.
Yes.
And then the actual discovery of changed the meaning of the word atom, because what we mean with atom today has nothing to do with what they meant. But at least that thought process can take centuries. So I agree, we should not be close-minded. Yeah. But at some point, someone has to write the check for how much money we're going to give to these string theories. So this debate has to happen. But I agree with you, we have to be open-minded to different approaches. Right.
I don't know if I answered your question.
Yeah. Good. Nick, do we have time for one more question, two more questions? You are the master of time.
Am I the master of time? Let's check. Yeah,
couple more questions? Okay. Yes, just next to you, Nick. No,
sorry?
Next to you in the front row. Oh, did you? Yeah. The lady next to you.
Right there, okay. I'm sorry. I can see your hand raised.
It's not a question, but just a humble point of view. I think, I believe, that mathematics is language of nature. Mathematics is physics, mathematics is economics, mathematics is chemistry, philosophy, art. So for me, it's like God. God is everything, everyone, but in everyone there is God. So it contains everything, but everything contains God. So it's paradoxal, and I don't know what you think about this.
Well, it's a lovely point of view. On a lot of these questions, I take these as poetic images, and if this is your inspiration, that's wonderful. I don't think one can criticize different people's spiritual inspiration, you know. So you're a mathematician, and you love mathematics, and you love God, and to you they are very closely related.
Yeah.
Well, I think that's
point of view.
That's beautiful. Right?
Thank you.
At the foundation of it, there's that awe. I think even the word God, everyone has different definition of it, but there's this aspect of awe.
Yeah, well, the ancient Greeks, I think, said, was it Fuad who said this? No. In mathematics, was it Plato? You think like the gods because you have absolute certainty. And it's the only area because everything else is empirical. So it's doxa, it's opinion. But mathematical reasoning gives certainty, I think was the view. So it's a glimpse of how the gods think. I think this was a point of view of some ancient Greeks, if I'm not totally mistaken, which is related to your comment, I think.
Okay, one more question, yes?
Thank you. Yeah, thanks for an amazing discussion. I have a question about size. So you said that sort of your best fit algorithm that best represent your data is the smaller, most compressed one. And I find that quite compelling, and maybe it's a very, very naive question. But if we think in other fields that I'm maybe more familiar with, like statistics, likewise, when you run a model and you're comparing different models and you have all these methods to compare the models, they're also somewhat based on size. So things like information criteria, you look at the probability of your model showing your data, but based on how many parameters you include, so that's also size. Genetics and biology, the DNA is a tiny, tiny thing. So what is it about size that makes it, like small size, that makes it sort of very good at, so is it about how easy it is to transmit the information, or?
The basic problem, yeah, these ideas are all related, and there are people who've used stuff very closely related to what I was talking about as an approach in statistics. I can't remember the name. Minimum description length, was it a gentleman in New Zealand? There are different people. It's all related. Why is the smallest program, why is the minimum amount of information important? Well, the basic reason is because if you allow too many parameters, you can always fit an equation to the experimental data. So that doesn't tell you anything, you know. Or as Enrico Fermi said, some young physics PhD came to him with a wonderful equation he had discovered that he felt, accounted very closely numerically for a whole bunch of experimental data. And Fermi looked and he said, oh, you have 5 free parameters. With 5 free parameters, I can fit an elephant. You know, so that's the problem. That's why a smaller number of parameters is more constraining, more surprising, and more likely to say something about the physical system, not about your model. You see, I think that's the basic reason. And it applies in statistics, actually, similar principles. There are a lot of ideas that are all connected. Another thing that's connected is Boltzmann statistical mechanics, which is particularly close to Shannon information theory. They're both ensemble theories of information, actually. Entropy is very close to information. And I don't know if it was von Neumann, or was it Shannon who went to von Neumann and said, what should I call this? And von Neumann said, call it entropy. That way no one will understand what it means. But actually it's a good suggestion because the mathematics is analogous in Shannon information theory and in Boltzmann statistical mechanics. And in statistical physics, you talk about entropy. So it is they're all related. They're different kinds of information theories, really. And in statistics also, ideas like this are.
So entropy because of the organization of entropy, is that what you...
Well, something with small entropy has less information content, than something with high entropy. I think these ideas are connected, actually. One could write a book on the history of these ideas. Another book you could write on the history of the notion of randomness. There are many different versions of it, and it would be an interesting history of ideas. It would require a lot of research. You go back to the ancient Greeks and other cultures, and randomness comes from the Arabic, right? Hazard is dice, right, in Arabic, if I'm not mistaken.
Nerd is Arabic, probably related. Azar, nerd. Nerd is a dice.
It's different?
Happenstance?
Yeah, well, anyway. So it's these ideas, in French it's aléatoire, which comes from dice in Latin. And I thought someone told me that in Spanish, azar comes from
probably
the Arabic
word, zahar, which also means
happenstance.
Chance.
Chance
yeah.
in Arabic.
Probably.
Yeah. So there's a very rich
yeah.
history in different cultures of these ideas.
Thank you.
Good. Yeah. One last question. Yeah.
Yeah. I'm curious with regard to. Whether we can recursively apply what you did with the algorithmic information theory, meaning that you find an algorithm to replicate data, the smallest one, or can you apply the same concept on the algorithm? Is there something that could replicate the algorithm? I don't know if that makes any sense, but if that's possible, can you do this recursively? And if that's possible, where do we go? I mean,
no, it doesn't. It doesn't get any smaller. Once you have the smallest program for something, that cannot be compressed any further.
The program itself is made of bits, so at the end of the day, whether it's an algorithm or just data, is the same thing.
Yeah, it becomes
Same
incompressible at that point. But I think also you may be asking the question, can these ideas have any practical application? Which is a good question. Now, I don't know anything about that. People like Hector Zanil have looked for versions of these ideas that have practical applications. The application that interests me is philosophical, that this gives you a different perspective on incompleteness and on Gödel's incompleteness theorem. The fact that you can't prove that you have the most concise program, I think is, I find it astonishing that such a simple question can be shown to be intractable with any mathematical theory. There are more precise statements of these things that you can find in my Institute for Advanced Study book, Philosophical Mathematics, if you're interested. It's only 68 pages, but it's not easy reading.
Great. And Gregory has written a number, actually, of books that are popular books, like anyone can read from high school above.
I tried.
Yeah.
I tried.
So yeah, I encourage all of you to go and read the literature that he has written. It's amazing. The journey has been amazing today. We have touched on so many areas, which is the definition of transdisciplinarity. And it was very fascinating. So we did, what did we do? Computer science, we did philosophy, we did some biology, we did some physics, we did some anthropology. What else? Some history of science, history.
Well, I hope we had some fun. I thank all of you for coming here. Thank you for the good questions. Thank you for your interest. I'm sure there are more fun things to do in Rabat than be here listening to us. But we are grateful to the Institute for Advanced Study and to UM6P for hosting us and our two little children and permitting us to devote ourselves to developing these ideas. Virginia has a book in progress. I have a little book that I managed to complete in 5 months here at the Institute for Advanced Study. And this book would not have seen the light if it weren't that we were invited here. So thank you. Reda is the original contact, the reason we're here. If it hadn't been for him inviting us to the Science Week last February of the previous year, we wouldn't be here now, and we've enjoyed it immensely, including this interaction with Najib and with all of you. So we're very happy to be here and exchange ideas with all of you. Thank you very much.
Thank you. Thank you. All right, Virginia, one more word, and then I give the mic back to just a closing, unless you agree with everything that he said in his closing remarks. So just one more word, last word, and then we can wrap up and give back the mic to the masters of the event.
Yes, well, being thankful is the great message, but you know, the real spirit of us being here together is that we do this many more times, and that we take the memory of this pleasant, interesting, intriguing moment so that we can replicate this. You know, Greg was referring to the IAS, to the UM6P, to the Chair of Complexities and Humanities. There are young people here, and we want you to create UM6Ps, IASs, Chairs of Complexities and Humanities. What I feel is that what we want this to replicate, to grow in, not as a copy, obviously, in a creative fashion, but we want to continue this tradition of exchanging ideas with pleasure. This is what I would have to say.
Thank you.
Thank you.